The star is swinging around nothing. Astronomers point their instruments at a bright sun about 1,560 light-years from Earth, and they watch it wobble. Something is pulling on it, something with the mass of 10 of our suns. But when they turn every telescope humanity has ever built toward the space it is orbiting, there is nothing there. No light, no heat, no radio whisper, just a gravitational anchor sitting in the dark, dragging a living star in circles around it. That object has a name, Gaia BH1. And the reason NASA and the European Space Agency are speaking about it in words like unusual and intriguing is that its existence forces a question no one wants to ask out loud. How many more are out there, and how close? Because here is what the press release did not say. Gaia BH1 is not alone. Astronomers have found 2 more, 3 dormant black holes, hiding in plain sight in our stellar backyard, discovered only because they happened to be tethered to visible companion stars we could watch move. And here is the part that should already be bothering you. The theoretical models, quasi-stars, Thorne Żytkow objects, endoparasitic accretion systems, say a black hole can sit inside a living star, inside its outer envelope, feeding slowly, invisibly, for millions of years. And from the outside, that star will look completely normal. Wherever you're watching this from tonight, do me a favor. Walk outside later, look up, and ask yourself honestly, did you ever think the darkness between the stars might not be empty, but occupied? Because that is the version of the sky we are now living underneath. And the discovery, the real discovery, is not that we found one. It is that we finally proved we cannot tell which stars already have one inside them. The official language is careful. The math underneath it is not. Here is what they are actually telling us. And here is what they are not. The official story you are being told right now sounds like this. Scientists have made an exciting new observation. A rare and unusual object has been detected. It offers valuable insight into stellar evolution. Every word in that sentence is doing quiet, careful work. Read it slowly. Rare, in a galaxy with 400 billion stars, does not mean few. It means millions we have not yet found. Unusual in the vocabulary of a peer-reviewed astronomy paper does not mean quirky. It means our existing models did not predict this, and we are scrambling to update them. And exciting, in a press release, almost always translates to a much less comfortable phrase inside the actual publication. That phrase is, we did not expect this, and we do not yet fully understand what we are looking at. This is not deception. This is translation loss. But the loss is not random. It runs in one direction. The public version is always calmer than the paper. Compare the headlines to the abstracts. The headline says a new black hole has been discovered. The abstract in Nature or monthly notices of the Royal Astronomical Society describes a statistical revision, a re-estimation of how many dormant compact objects likely populate the Milky Way. Those numbers are not small. When LIGO detected its first black hole merger in 2015, the public heard a triumph. What astronomers heard was that stellar mass black holes were far more common and far heavier than the old models predicted. Every subsequent detection has widened that gap. The public trusts that scientists know what is out there, but the honest answer is that astronomers largely know what emits light. And the objects we are now talking about, the dormant ones, the silent ones, the ones already inside living stars, emit almost nothing at all. Think about what that means for a moment. The sky map you were taught in school is a map of the noisy. The dangerous residents of the neighborhood have never been on it. To understand what a black hole inside a star even means, you have to understand what a star actually is. And that is where the comfortable picture starts to fall apart. A star is not a solid object. It is not a light bulb hanging in the sky. It is a war, every second of every day, in the core of every star you have ever seen, gravity is trying to crush the object out of existence, and nuclear fusion is pushing back with just enough force to hold the collapse at bay. That balance is called hydrostatic equilibrium, and it is the only thing keeping stars from imploding within minutes. Our own sun, the warm, familiar thing you have taken for granted your entire life, is running that war at a core temperature of roughly 15 million Kelvin. That is about 2,500 times hotter than the inside of an industrial blast furnace. A pinhead of that core material teleported to the surface of the Earth would incinerate everything within 100 kilometers before anyone had time to notice. And this is the quiet, stable, well-behaved state of our star. This is the version we depend on for every warm afternoon, every crop, every heartbeat. Every sunrise you have ever seen is proof that gravity has not yet won that fight in the sun's core. Not a metaphor, a physical fact. Now here is the part that should sit heavier than it usually does. That balance is not a fact, it is a negotiation. A star is not something that is stable. It is something that is being held stable, moment by moment, by a violent internal process that has to succeed continuously for billions of years. Fusion pressure pushing out, gravity pushing in. Match those forces to within a fraction of a percent. And you get a sun, miss by too much, and you get either an explosion or a collapse. There is no third option, and the moment fusion falters, the moment the hydrogen runs low, or the core cools, or the internal structure loses its balance, gravity does not hesitate. It wins, instantly. Now think about what that means. If something else is placed inside that balance, something denser than fusion pressure, something that eats mass and never gives it back, it does not have to be violent to be catastrophic. It only has to be patient. Now insert something like that into the core of a star. What happens? That is what a black hole inside a star actually does. It sits, it feeds, and it waits. The accretion is slow because the black hole is surrounded by dense stellar plasma that cannot fall in faster than the physics allows. From the outside, the star continues to shine. Its spectrum shifts subtly. Its rotation changes gradually. Its luminosity fluctuates in ways that, without a comparison model, look almost normal. This is why the Thorne-Żytkow object theory, first proposed by Kip Thorne and Anna Żytkow in 1975, has been so hard to confirm. The candidates, HV2112, HV11417, show anomalous spectral lines, unexpected traces of lithium, rubidium, molybdenum, elements that should not be there at those concentrations in ordinary red supergiants. But you have to know exactly what to look for. And even then, the signature is subtle enough that arguments in the astronomical community have run for years over whether these objects really contain compact cores or are simply unusually enriched normal stars. Some models suggest a compromised star can maintain a nearly ordinary appearance for millions of years before the internal parasite finally consumes enough mass to end the negotiation. Millions of years. That is the timescale of a fossil, not a warning. It means a star that already contains a black hole today might not visibly reveal that fact for longer than our entire species has existed. It means the light you are seeing right now from a nearby red supergiant left that star at a moment when it was already compromised, and we have no way to tell. It means when we finally do detect a change, the change will have started so long ago that we are watching history, not present. Think about the implication. Astronomers have cataloged hundreds of thousands of stars in our local neighborhood. They have taken their spectra. They have measured their masses. They have written them down in databases and called them known. But there has never been a reliable test, never, to determine which of them might already have something at the center that is not hydrogen. It is like discovering that some percentage of the buildings on your street have a slow, invisible structural failure. From the sidewalk, they look identical to every other building. The doors work, the lights are on, but the load-bearing beam at the center is being eaten from the inside by something you cannot see from the street. The only way to know which ones are compromised is to wait until one of them collapses. And in astronomy, one collapsing means a supernova. It means a burst of energy that, if it happens close enough to Earth, would not be a curiosity. It would be an event. One hidden black hole in one star is unsettling. But astronomy does not deal in ones. It deals in populations. And that is where this stops being a curiosity. Here is the math that breaks the fantasy. We have directly confirmed roughly 20 stellar mass black holes in our entire galaxy. 20. The Milky Way contains 400 billion stars. The current statistical estimates, based on Gaia's data and the work of astronomers like Karim El-Badri and his collaborators, suggest that the true number of stellar mass black holes in our galaxy is somewhere between 100 million and 1 billion. Let that sit for a second. We have found 20. There are, conservatively, 100 million. That is not a discovery gap. That is a rounding error. Every star chart, every map of the local stellar neighborhood, every visualization of what is around us. It is a map of the lit portion of the room. The furniture is still there. We just cannot see it, and the ratio should shake you a little. For everyone we have found, there are 5 million we have not. Now scale that forward. If even a small fraction of massive stars host a hidden compact object at their core, the number of potential future collapse events in our galaxy alone climbs into the tens of millions. And here is the number that should really bother you. Statistical modeling suggests that within 1,000 light-years of Earth, there may be somewhere between 5 million and 10 million dormant black holes. 5 to 10 million. Within 1,000 light-years. A handful of them could plausibly be closer than the Alpha Centauri system, which is about 4 light-years away. And we would not necessarily know. We have not surveyed them. We have surveyed the ones that scream. The intuition most people have, that if something big and dangerous were close, we would obviously know about it, is comforting and wrong. Distance in astronomy is measured by light. Objects that do not emit light do not participate in the measurement. So what does one of these actually do if it does not stay hidden? What does the failure mode look like when a compromised star or a wandering dormant object decides to stop being quiet? A dormant black hole does not need to hit anything to end life on Earth. Its gravity alone, passing through the outer solar system, could destabilize planetary orbits within a single human generation. It would not need to touch us. It would just need to walk past. The Oort cloud, the shell of icy bodies at the edge of our solar system, stretching outward for perhaps a full light year, would be gravitationally stirred, sending waves of comets inward over the course of decades or centuries. Some of those comets would find planets. Not all of them would miss. Even a modest perturbation of the outer solar system, from a dormant object passing at a distance we would still consider astronomical, could rain impacts down on the inner worlds for tens of thousands of years afterward. There is a hypothesis, still debated, that periodic mass extinctions in Earth's fossil record correlate loosely with the sun's oscillation through the galactic plane, a region where dark objects might be more densely packed. We cannot prove this either, but the mechanism, again, is not exotic. It is simple gravity, operating over long enough timescales. And a nearby collapse event, a supernova, or worse, a hypernova, from one of these compromised massive stars, could sterilize the biosphere from hundreds of light years away without ever emitting a shockwave that reached us, because it would not need to. What would reach us is the radiation. Space is big, but it is not big enough that far away always means safe. The best current models suggest that a gamma-ray burst pointed at Earth from within about 6,000 light-years could strip the ozone layer in under 10 seconds. 10 seconds. That is less time than it takes to read this sentence. Now translate that. The ozone layer, if you compressed it to the atmospheric pressure at sea level, would be about 3 millimeters thick. 3 millimeters. That is thinner than a stack of 2 credit cards. That is what stands between every living thing on the surface of this planet and hard ultraviolet radiation from stellar catastrophes happening in places you cannot see with your eyes. Everything you love, everything you have ever cared about, every forest and coral reef and human city, is protected from cosmic sterilization by a shielding layer thinner than the edge of a coin. There is a hypothesis, taken seriously by paleontologists and astrophysicists, that the Ordovician mass extinction, an event 445 million years ago that killed roughly 85% of marine species, was triggered by a nearby gamma ray burst. We cannot prove it. The evidence is circumstantial. But the pattern of the die-off, the specific damage to shallow water organisms with the least protection from UV, fits the model too well to dismiss. It has happened before, or something very much like it has. The mechanism exists. The only question is frequency, and that is a question we cannot yet answer because we cannot see the objects that would cause it. Which brings us to the deeper problem. Every observation tool humanity has ever built, Hubble, JWST, Chandra, the Very Large Telescope, ALMA, all of them, was designed to detect things that do something, things that emit photons, things that pulse or glow or radiate or absorb light against a brighter background. Dormant black holes do almost nothing. They are, by their nature, the quietest objects in the universe. We built the entire apparatus of modern astronomy around emitted signals, and then discovered that the most gravitationally dangerous residents of our galaxy are the ones that emit nothing at all. Gaia's astrometric method, measuring the tiny wobble of a visible star as it orbits an invisible companion, is currently the only reliable way to detect these objects, and it only works when the black hole happens to be paired with a visible star close enough that the wobble is measurable. Isolated dormant black holes, drifting alone through interstellar space, are essentially undetectable with current technology. LIGO can hear them when they merge. It cannot see them when they wait. Every other instrument is blind to them, everyone. This is the astronomical equivalent of a blind spot the size of the sky. Before Karl Jansky pointed the first radio antenna at the heavens in 1932, we thought the universe was quiet. Then he turned it on, and the galactic center was screaming. Every generation of astronomers learns the same humbling lesson. The sky they thought they understood was mostly invisible to them. Before infrared astronomy, cold objects were hidden. Before X-ray astronomy, the high-energy universe was hidden. Before gravitational wave astronomy, colliding black holes were hidden. Each new window revealed a cosmos more crowded, more violent, and more populated than the one we thought we knew. And each time, it took the astronomical community roughly a generation to fully absorb the implications. We are early in that same process now with respect to dormant compact objects. The window has just cracked open. The full picture is still years away. And the interval between crack and full picture is precisely the interval in which decisions get made about which instruments do or do not get funded, and the tools that would let us actually map the dormant black hole population at civilizational scale. Dedicated wide-field astrometric successors to Gaia, gravitational wave observatories 100 times more sensitive than LIGO, space-based interferometers spanning millions of kilometers, do not currently exist. Some of them are proposed, some are funded partially. Some have been on the wish list for 2 decades. And the funding curves for basic astronomy, in real terms, have been flat or declining across most major agencies for years. So why is none of this being said clearly? Why does the public still hear discovery? When the researchers are quietly writing, "We did not expect this, and we do not yet understand it"? The answer is not conspiracy. It is far more mundane, and in some ways more troubling. Space agencies, observatories, universities, and the scientists who work inside them are not lying to you. They are managing tone. Careers depend on funding. Funding depends on political support. Political support depends on public enthusiasm. Public enthusiasm depends on wonder, not dread. So somewhere between the peer-reviewed paper and the press release, and again between the press release and the news headline, the sharp edges get sanded off. The uncertainties get softened. The unsettling implications get compressed into words like fascinating, intriguing, remarkable. If you compare the abstract of the Gaia BH1 discovery paper, a genuinely careful, technical, cautious document, to the mainstream news headlines that reported on it, you can watch the tone shift in real time. The paper describes an object that challenges standard models of stellar evolution and binary black hole formation. The headlines describe a cool space find, same object, two different emotional realities, and the audience only ever sees the second one. This is why so many people are perpetually surprised by scientific news that specialists have been quietly worried about for a decade. It is not that the information was hidden, it is that the emotional signal was compressed on the way through the pipe. This is not new. When the Chicxulub impact crater was first proposed as the cause of the dinosaur extinction in 1980, it took nearly a decade for the public framing to catch up with what the geologists already knew. When the ozone hole was first measured over Antarctica, the initial official statements downplayed the severity for years, while behind the scenes, atmospheric chemists were writing terrified memos. When climate scientists began publishing their sharpest warnings in the 1990s, the public communication was consistently, deliberately calmer than the underlying data. There is a pattern. The audience is always about 10 years behind the researchers in emotional understanding of what the data actually means. And to be fair, because it matters to be fair, this is not because scientists are hiding a catastrophe. It is because science, as an institution, has learned the hard way that fear does not produce funding. Wonder does. Curiosity does. Fear tends to produce disengagement, or worse, political backlash. So the messaging is calibrated for engagement, not for accuracy of emotional weight. The problem is that by the time the public framing catches up to what the researchers already know, the window for building the instruments to actually study the problem may have already closed. And when you follow the unsanded version of this story to its endpoint, you stop dealing with a story about one weird star. You start dealing with a story about the universe itself. Because a black hole inside a star is not really the discovery. The discovery, the one hiding underneath the headline, is that our 400-year-old model of the galactic neighborhood is wrong in a specific direction. Ever since Galileo, we have built our picture of the cosmos around bright objects in a mostly empty dark. Stars, planets, nebulae, galaxies, luminous things scattered across a passive vacuum. That picture is comforting because it implies that what we see is what is there. It is also, we are now learning, incomplete. The dark is populated. It is populated by things that outweigh us by factors of millions. And the population is not small. It is not scattered. It is not distant. It is here, all around us, in the same volume of space we have always considered home. We do not live in a quiet suburb of the Milky Way. We live in a lit clearing inside a dark forest, whose shape we have never mapped. Read that sentence again. That is the sky, honestly described. Now think about what that means for every larger question. The Fermi paradox, the puzzle of why we have not detected other civilizations, takes on a different weight when you realize that the safe evolutionary windows for complex life in any given region of a galaxy may be narrower than assumed, because the gravitational and radiation hazards from dormant compact objects are far more common than the previous models allowed. The rare Earth hypothesis, the argument that Earth-like planets with stable biospheres are astronomically unusual, becomes harder to dismiss. Maybe civilizations arise often. Maybe most of them do not get billions of quiet years to develop. Maybe the neighborhood is louder than we knew. The comforting picture of Earth as a stable planet in a stable orbit around a stable star inside a stable region of a stable galaxy is a nested set of assumptions. This discovery breaks the innermost link in that chain. And once the innermost link is broken, every link above it is under review. This is the astronomical equivalent of germ theory in the 1860s. Before Pasteur and Koch, physicians washed their hands in dirty water and delivered babies with unwashed instruments and could not understand why so many mothers were dying. The problem was not that the pathogens were new. The pathogens had always been there. Humanity had lived alongside them for our entire existence. The problem was that until we could see them, until we had a microscope powerful enough and a theory clear enough to interpret what the microscope was showing, we could not know what we were living with. The doctors were not stupid. The tools were not there. And once the tools arrived, the world did not become more dangerous. It became more honest. That is where astronomy is right now, with respect to the dormant compact object population. The objects have always been there. Every night sky your grandparents ever looked at, every star chart drawn by every culture in every century of recorded history was already like this. The difference is that now, finally, we're starting to be able to see them, and knowing changes what it means to look up. So where does this leave us? Not with an apocalypse, with something quieter and in some ways worse. Here is the verdict. The universe is more crowded, more armed, and more indifferent than the versions of it we grew up with. The sky we were taught about in school, bright and empty, distant and safe, was a partial map, drawn only from the objects that happened to emit light. The real sky, the one we are only now beginning to measure honestly, contains hundreds of millions of silent, massive, gravitationally dangerous objects hiding in the dark between the stars we can see. Some of them are, statistically, closer than we have said out loud. Some of them are, right now, sitting inside stars we call ordinary, feeding slowly, invisibly, patiently, waiting for a collapse that may be thousands of years away, or may have already been triggered in ways whose light has not yet reached us. NASA did not find a black hole inside a star. They found the first one they could prove. That is a very different sentence, and the difference matters more than the announcement did. None of this is a call to stop exploring. It is not a claim that scientists are incompetent or that agencies are lying. It is not an argument that the discovery is bad or that research should be defunded. The opposite. The only way out of this, the only way to actually map the dark population, understand the risks, and give humanity a real picture of the neighborhood we live in, is more science, not less. More honest science, more sensitive instruments, more willingness on the part of the institutions that fund and communicate this work to tell the public the harder version of the story. Because the public, given the harder version, has historically funded the harder work. That is the narrow hope in all of this. The same tools that revealed this hidden population can, if built at civilizational scale, map it. We are not helpless. We are just, for the first time in history, honest about how much of what surrounds us we still cannot see. So walk outside tonight, look up, find whichever bright star catches your eye first, and understand that you are seeing the version of it that photons allow you to see. Understand that somewhere in that same field of view, statistically, there are dormant objects with the mass of many suns, drifting through the dark, invisible to every instrument you or I have ever heard of. Understand that some of the stars you are looking at right now may already have something inside them that is not hydrogen, feeding slowly, waiting. Not tonight, not this year, not in your lifetime, probably. But on a timescale the galaxy considers ordinary. That is the honest version of what you are looking at. The star is swinging around nothing. You know now what nothing means. It means the sky was never what we labeled it. It never was. We just could not see it. And the strange thing, the thing that stays with you after this video ends, is that this changes nothing about the universe. It only changes what we are willing to admit we are living inside. That is the discovery, not the black hole, the mirror it held up to the map.